I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day I die. No one really knows why gravity exists.
Good evening. Good evening, everyone. You can set your watches by the start of a Wonderfest event. Thank you for being here. Here at Hopmonk for the Bay Area Beacon of Science, that is Wonderfest. My name is Tucker Hiatt. I'm the founding director, and I'm grateful to see you here. Thank you for coming out. Okay, tonight's Wonderfest speaker is Dr. Ellie Tubman, assistant professor of nuclear engineering at UC Berkeley. Go Bears. Ellie hails from the United Kingdom, where she earned a Master's of Physics degree at the University of Sussex, and then a PhD in physics at the University of York. As a professional physicist, Dr. Tubman became a research associate at Imperial College, London. Then she came west, way out west, here to California, in fact, to the Lawrence Livermore National Lab, with its famous research center for laser-driven fusion, the so-called National Ignition Facility, NIF, a very nifty name, yes. Ellie would then return to England briefly for a year to lecture at Imperial College, London, and then she's now back in the Bay Area as a tenure-bound, I suspect, professor at Cal with her teaching and speaking skills well honed, and we will be the beneficiaries of that tonight. Please welcome, to discuss the promise of fusion power, UC Berkeley nuclear physicist, Dr. Ellie Tubman.
Thank you so much for the introduction and also for inviting me here this evening. And thank you for coming along. I hope that I can teach you something about fusion. Maybe some of you already have an idea of what fusion is and what's going on in the field. But hopefully I can give you some little insights as to where we are currently, and also maybe, some ideas of where we're going in the future with this. And I thought it was very apt to put here the future of fusion energy on tap being in a brewery this evening. Before I begin, you have also already heard a little bit about myself and my background, but I thought I would just give a little bit more of a dive into who I am as well. So in terms of my journey to where I am now, I knew sort of at secondary school, I guess high school here, that I found science really interesting. So there's a photo of me up in the middle here in a science lesson when I was about 15 years old. We were investigating water wheels and I loved asking questions. Loved trying to figure out what was going on. So really enjoyed science, really enjoyed asking questions. I actually didn't have parents who went to university, so I was the first generation to actually go. When I told my parents that I was going to do physics, they were like, why aren't you going to go and study maths? Like, you're really good at maths, like, and that could give you jobs into finance or, into something where there is a very obvious career path. Why are you doing physics? And I think slowly as we started to explain and explore the options in physics, suddenly they realized, even if you did physics, you could go off and do finance. Or maybe I get sucked into doing the research side and stay in research. So I went to study at the University of Sussex, which is down on the south coast, just outside of Brighton in the UK. I actually didn't work on fusion at all in my undergraduate. I was investigating supersymmetrical particles, working on one of the Atlas detectors over at CERN. So I was actually based at Sussex, but looking at lots and lots of histograms of data. It was all very computational. I wanted something a little bit more experimental, a bit more hands-on. So I graduated and then moved up to the University of York. So I went up to the north of the UK, where I studied at York on this fusion program. Absolutely loved it, and so then continued on, moved back towards London. So I grew up down in Dover, or down near Dover here, went to University of Sussex here, up to the north, back to the centre to London, where I then was a postdoc at Imperial College working on the Magpie machine, which is actually a pulse power machine that was originally set up also to do fusion. So there are lots of different approaches to fusion, as we'll explore through this talk. And pulse power is one way. Actually, I won't be talking a huge amount about pulse power today, but it is an approach that if you want to talk about later, we can discuss in more details as well. So I spent 3 years in London, then moved over to Lawrence Livermore National Laboratory to work on the NIF. I moved in March of 2020, which I don't know if anyone remembers that time of year. Great time to move internationally. Yeah, IKEA shuts, it turns out, in a pandemic, and trying to furnish an apartment when IKEA is shut is hard. But anyway, I loved working on the NIF. I also did experiments over on, there's an omega laser over in the University of Rochester that I did some time over on as well, investigating various aspects of fusion. I then got a job back at Imperial College in London, working as an assistant professor there. But the Bay was calling to me, and so then moved back and took a position where I am now at Berkeley just last year. So now I'm setting up my group. And as a little bit more of an aside, these are some of the things I get up to through research and also outside of research. So there have been conferences that have been held in ski resorts. There have been summer schools I've been to in Crete, which have been wonderful experiences, great times to meet other collaborators, other researchers in the field. I'm also a keen cyclist, keen sailor, as you can see down at the bottom right here. Up in the top right, this is now the starting of my research group at Berkeley. So these are some of my undergraduate students. We went up to explore one of the labs, the laser labs up at Berkeley National Laboratory as well. And this is my little companion at home, Zeely, my house rabbit. So yeah, she's very cute. Anyway, that's a little bit about some of my background. Yes.
Are you too modest to tell us that you are a triathlete?
Well, that's, yes, okay. I also really enjoy triathlons. So the cycling has led in, well, I was always a runner as well. Didn't really enjoy the swimming, but turns out you have to do that bit as well with a triathlon. So, okay, I'll do some swimming. So yes, I also enjoy triathlons. It's important, I think, to be healthy outside of work as well as inside of work. It makes me want to come to work on Monday morning because as I've been sitting on the boat, there's actually a lot of synergies between fusion and between physics and hydrodynamics and flows that happen in sailing that also can be applied to plasmas and to fusion physics as well. That actually there's people who've designed simulations of the bay and the models of water movement that actually there's a lot of comparisons that you can make between those as well as how you would set up a simulation of a plasma of these fusion environments as well. So yeah, I love all of these things. They keep me going to do a bit of both. Okay, so what are we going to talk about today? Well, we're going to discuss firstly what is fusion, and then we're going to discuss, well, can it really provide us power in the future? What is it that we're trying to achieve by building these fusion power plants? What is the demand that we're going to be needing to meet? And then I'll also discuss a little bit about, well, what is the state of the field at the moment? And field can also be taken a pun there because we use magnetic fields in some fusion applications as well. But firstly, let's touch on, well, why are we trying to investigate fusion? Why do we need these other power sources? Well, in 2023, the world's global energy demand was 172,400 terawatt hours. And this is not even accounting for everyone in the world actually having access to electricity and having access to being able to use these power sources. So what happens as these countries start to develop and more people put demands on our power grid? And actually, one really big topic at the moment is, well, what's happening when we've got all these AI sources coming up that are also demanding so much of the power grid? So ChatGPT, if you run a search in it, it takes 2.9 watt hours of electricity in comparison to Google search, I guess before they also had their AI tools, would only use 0.3 watt hours. And so our demands on power to be supplying these data centers is only going to be growing from here on in. it's a really, really exciting time to have these tools, but they do need to be powered as well. And so this is a graph down here in the bottom right showing projections out to 2030, and you can already start to see that these things are only going to be increasing in power consumption, and yeah, the rest of the world is going to be following along behind here as well. Now, if we actually look at where our energy sources are coming from currently, we can see that we're making up a lot of our energy from coal, from oil, and from natural gas. And I'm sure many of you know, but these are not an infinite resource. And also, we will want to look to alternatives because of the damage that they can do to our environment. So we've already started to include things like nuclear power already as part of our energy sources that are out there, but they're only a very small contributor up here. And nuclear power, when being included here, is obviously talking about fission. So why, looking at the different types of energy sources out there, why are we not going to be using or thinking about using maybe just wind power plants or solar power plants? So I've done some comparisons here, and so over in this table on the right we've got the amount of power that could be produced from a gas power plant if it were running at 500 megawatts of power being put out. Power plants, you have some sort of operational time associated with them as well. So this third row here is showing a percentage where for each of these power plants of how, during that whole year, how long is that power plant going to be operational for? So for gas power plants, you might have to have downtime to do some maintenance. Wind power plant, you've got about 40% operational time. The wind's not always going to be blowing. And again, you might want to do some maintenance, so 40% operational time. Solar panels, I've estimated here, are 20% operational time. Again, some of these numbers are going to depend on where you've situated these power sources. So for example, if you put a solar panel over in the UK, the operational time probably would be a lot less. And the wind power plant, if you put that in an area that doesn't get much breeze, then those are going to drop as well. But the other important thing to be considering here is actually the amount of space that these energy sources take up. And this starts to lead into, well, okay, how much energy are we getting out of these systems? So for a wind power plant, to produce 0.7 terawatt hours per year, you would need a area size, and this is accounting for spreading out your wind turbines, of 15 square miles. For solar panels, if you wanted to get 0.35 terawatt hour per year, so half of the wind power, you'd need 2 miles squares covered completely with your solar panels. And you can look at this for a nuclear fission power plant as well. So nuclear fission power plants give you an awful lot of energy out, and so you can again go to condensing these down to maybe 1.26 square miles. And these numbers perhaps aren't so useful to be showing in this form. What might be more useful is to take the number that we saw on the previous slide of the total world energy supply that we need, and see, okay, well, if we were going to supply the world's energy need using solely one of each of these four, how big an area are we going to end up covering? So let's start with taking a gas power plant. So a gas power plant, if you were going to supply the world's total energy, would need 13,000 square miles, i.e. basically the size of Maryland. So you'd cover your gas power plants over that state. If you were going to look at a wind power plant, then you would need to cover the whole of the USA to produce the world's energy demands. If you were going to look at solar panels, you would need to cover 4 times the size of Texas. If you were going to look at nuclear fission, then you would cover the size of South Carolina. So you can start to see where you might put emphasis on different technologies being developed. And fusion comes in very comparable to the size and the energy density, I guess, that you would get from fission power plants. So, and I'm not going to stand up here and say, oh, we should just be investing in nuclear power. I don't think that's going to be the story. The story is going to be having a combination and a balance of all these different technologies. Putting the solar panels where you get an awful lot of sunlight, putting the wind power plants where you get a lot of wind, and starting to use a combination of all of the different power sources that are out there. So I mentioned nuclear fission power plants. So, and often when things get referred to, for example, we've got the Diablo Canyon nuclear power plant here. We'll talk about a nuclear power plant and we're talking about fission. We're talking about a fission power plant. But technically fusion is also under that umbrella. It's also a nuclear process. Now, obviously there are downsides to fission power plants. There is radioactive, long-lasting radioactive waste that comes out of them. Fission as a process itself, you have a neutron coming in, hitting a nucleus, and it splits that atom apart. But it also produces more neutrons that then go on and do further interactions. So you're kind of creating this multiplying effect that, if you're not careful, can run away. They have a lot of controls out there now such that this isn't such a risk as one might imagine, but you're still producing more neutrons in the original interaction. Now, when I start to say the word nuclear, often nuclear is met as a topic with a lot of hesitancy. And I mean, I've even found that within my family and within the communities that I grew up in, that growing up on the southeast coast of the UK, so my parents' house, we are like 20 miles away from the Dungeness nuclear power station. And so I've grown up down the road from a nuclear power station. And you see within the community then there is talk and there is a fear around that. And if I were to say to you that in this room there is a virus, perhaps that might also put you on edge. And if I show you this photo where we've got this radiation symbol, that probably wouldn't be an area you want to walk into. And a lot of the fear, I think, around nuclear, and a lot of the research has started to point to, is that when you have something that you cannot see, you do not know the risk that you're putting yourself into. If there is a virus in this room, you don't know where that virus is. You don't know what quantity of virus there might be. There might only be 5 particles of virus around, in which case you're like, oh, that's probably not going to be a big concern. But if the whole room is full of a virus, then it starts to become more of a worry. And the same can be said for radioactivity, I think, that radiation is something we cannot see. We do not know when we're in an environment that is particularly radioactive and maybe then more dangerous for us. But actually, in terms of radioactivity, I think there's a lot of, I mean, if I were to talk to my parents, I don't think they would necessarily be aware of, well, what radioactivity is around us naturally. So actually living within 80 kilometers of a nuclear power plant for 1 year, you get a dose of 0.00009 millisieverts. In comparison, eating a banana gives you 0.0001 millisieverts. So eating a banana gives you more radioactivity, more radiation than living near a power plant would. And indeed, getting on a plane and travelling for 6 hours gives you 0.04 millisieverts. If you smoke, you're getting 36 millisieverts of radiation. And so there is a scale out there of obviously all of these different radioactivities. And actually in the US they set a safe dose, so people that are working in radioactive environments or dealing with radiation, the safe dose limit in the US is set to 50 millisieverts per year. If you were to get a dose of 25,000 millisieverts, that is essentially the rate that they are like, yes, at this radiation, you will get a 100% chance of getting cancer. Actually, at this, you're probably going to end up with a lot more severe issues, and you probably won't even get to the chance of developing cancer because that amount of radiation is huge. Now, your body contains carbon, which is also naturally radioactive. So you are actually naturally producing 0.5 millisieverts of radiation each year. If you live in Denver, then you are at a higher altitude and you're also living with uranium in the soil that gives a dose of 10 millisieverts per year. And if we looked at current statistics of actually, so a lot of the issues with radioactivity and a lot of the concern is, well, perhaps there is a risk of getting cancer. Well, for whatever cause out there, Currently, the statistics say that the population has a 40% of developing some sort of cancer. Let's have a look at Hiroshima, the nuclear bomb that was obviously dropped over there. Within 1 kilometre of the detonation, there was 4,000 millisieverts radiation level, so extremely high and deadly. But as you start to get away from this, a lot of the survivors, they estimated, actually had a 200 millisievert radiation level, which actually only increased the cancer rates by about 1%. And so a lot of the statistics out there, they are a lot to understand. But a lot of this is starting to point to that radioactivity, the public perception has almost put more of a negative spin on actually the realistic risk associated with it. And if you want to read a really good book discussing some of the or radioactivity and understanding nuclear more generally, I would point you to a book called Physics for Future Presidents, written by Richard Muller, actually another professor at UC Berkeley, who I hadn't come across until the last few months, but does an excellent explanation of talking through the different statistics to try and piece together, what is safe and what should we be worried about. I thought it was important to talk about nuclear when going out and talking about fusion, because the two are linked. And again, if we actually look at the amount of deaths that get caused from other energy resources as well, there's an awful lot of accidents that have happened, and this is actually normalized to the amount of power out there. So for example, there aren't that many nuclear energy power plants, but obviously there have been some incidents, but again, it's still lower amounts of deaths than for some of the other sources out there as well. So okay, so let's go back to fusion. So we obviously know that fusion works because we have a really good example of a fusion power plant that's up in our sky, the sun. The sun is at a temperature of about 15 million degrees centigrade, which is starting to lead on to some of the issues that we might start to encounter when we're looking at creating fusion here on Earth. We actually need to create an environment of 100 million degrees centigrade, so even hotter than the sun, because it's a game of statistics again. We have to heat things up to make the fusion reactions happen even more efficiently. The sun is actually really inefficient at producing energy. The amount of energy that it produces per volume is less energy than your body produces. So very inefficient. We need to do it better. We need to get to hotter temperatures, because the temperatures, as we'll see in a minute, start to help us get to these fusion conditions. Now, when we start to get to temperatures of 100 million degrees centigrade, we're not in a solid phase, we're not in a liquid, we're not in a gas, we're in a plasma. And a plasma is when you have this very hot ionized gas. You've essentially stripped out your electrons from your atoms. So you've got your electrons and you've got your protons and your neutrons separated. Now, we mentioned fission is when you're breaking apart those atoms. Fusion is combining the atoms. And there is a plot here that shows you atomic mass number on the x-axis and something called binding energy on the y-axis. But essentially this plot, when you've got all of these very, very heavy elements over on the right-hand side, you go up this curve. As you split them apart, you start to move to the left. As you start to fuse atoms, you start to increase their mass number and you start to move up towards the right. As you move in this direction, coming towards iron in the center, you're increasing the binding energy. And what this means is the amount of energy that is essentially released. So as you start to fuse elements, you start to release energy. As you start to break elements apart, you start to release energy. Why? Einstein. The E equals mc squared, that energy and mass are this interchangeable relationship. And when we combine two lighter when we combine two elements with lower mass numbers, and we'll come back to this deuterium and tritium, when you combine those together, they actually create you a helium and a neutron. And those particles are lighter than the two particles that came in to create them initially. So you have this energy mismatch, this mass mismatched, as it were. You've got heavier particles here, lighter particles here. Where did that energy go? They've still got the same amount of neutrons, protons that are making up these particles, but one is heavier than the other. And what's happened is that some of that mass that was over here has been released as energy. This E equals mc squared. Energy is being released from this mass. So when you actually put two nuclei together and try and smash them together to get them to stick and get them to fuse, they normally actually want to repel each other. So as I said, we've stripped the electrons off the outside, we've just got protons and neutrons now. Those protons are making that overall nuclei positive. And when you bring protons together, when you bring two things with the same charge close together, they're going to try and push each other apart. They don't want to stick together, they want to go off to the other side of the room. So we've got to give them enough energy, enough temperature to overcome those forces that are trying to push them apart and make them stick. And when you do get them sticking, if you have this tritium and this deuterium atom, which are actually what we call isotopes of hydrogen, so they have the same number of protons, different number of neutrons. When those two isotopes of hydrogen come together, you end up producing this helium particle and this neutron, and you also get energy. And the energy gets carried off by this neutron. And so that energy, that energetic neutron will fly out of your interaction, and that's the bit that you want to try and capture to then drive your steam turbines, which we will come back to shortly as well. And just as a very quick aside, I don't know if any of you have been to the Stern Grove Music Festival, but I was actually there on Sunday, and some very apt lyrics, and I'd hope to put a little video of this song being sung, but I'm so happy doing the neutron dance, and I'm just burning doing the neutron dance. These neutrons are super important. These are lyrics by the Pointer Sisters. It was a lot of fun. Would highly recommend if anyone hasn't been there. Thought it was fantastic. But anyway, so these neutrons are coming out with all this energy. They are the important part of this fusion reaction in harnessing those neutrons to then be able to get our energy out. So where are we going to get this deuterium and tritium from, these hydrogen isotopes? Well, you can produce tritium from lithium. So tritium isn't that abundant naturally. It's only got a half-life of 12 years, which means it's constantly decaying. And decays into other atoms that, it means it's no longer in this tritium form anymore. But with lithium, what we can actually do is bombard the lithium with neutrons, these neutrons coming out of our fusion reaction, to help us make tritium. So if you had the amount of lithium that gets contained within a laptop battery, and if you took a bathtub or half a bathtub of seawater, which will give you deuterium hydrogen isotopes, because actually it turns out that 1 in 6,000 hydrogen atoms within seawater are actually deuterium, you can then get the amount of material, the amount of fuel you need for one person's 30-year supply of energy. Actually, these numbers probably need to change a little bit if you're using a lot of AI. But anyway, that gives you a sort of baseline. So, okay, we've now seen that we've got this fusion source. It's going to be pretty safe because as soon as you cut the fuel off, as soon as you cut off the deuterium and tritium to your fusion reactor, that's it. There's no more fuel, so the reaction stops. So it's pretty safe. There is some radioactive waste that comes out, but not as large and not as long-lasting as you would find in a fission reactor. You're not producing greenhouse gases. It can be a very flexible and accessible energy source. You're not relying on the sun to shine, you're not relying on wind. You can also have these power plants around the world, assuming that they can get hold of lithium and of deuterium from the seawater, and you can produce it on demand. Okay, so let's get cooking. We've got the recipes, let's do this. The challenge is that when you created your plasma and you're trying to get these fusion reactions going, as I said, they want to repel, they want to be on the other side of the room. So how are you going to make everything actually stay together? Well, there are 3 ways that I'm going to talk about. Oh, well, actually, I'm going to talk about 2. You can use gravity, which is what the sun does, to make everything stick together and keep those atoms in the same environment such that they might interact with each other. Because all you're really trying to give them is a space that, once you put all your plasma into that, they're there for long enough that they are going to run into and fuse with another atom. That's really what we're trying to achieve here. So we're not really going to be able to use gravity in our reactors on the Earth. You could also use an approach called magnetic confinement fusion, where you're using magnets to confine your plasmas, or you can use inertial confinement fusion, which is where you're using lasers or X-rays to start heating your fuel. But then actually it's the fuel mass, it's the inertia, it's the unwillingness of that mass to move that will be helping us give our confinement as well. So let's start by just having a quick look at magnetic confinement fusion. So as I said, magnetic confinement fusion, you're using magnetic fields to actually restrict the motion of the fields. So plasmas are charged, you've got electrons, you've got ions, you've got positive charges, and as soon as you put something that's charged into a magnetic field, they like to follow the magnetic field lines. The magnetic field lines apply a force to them, and so you can actually use those forces to be keeping your plasma in one place. And so we have a design called a tokamak, which is essentially a donut shape. And so you can see a diagram over on the left-hand side here, where we have 2 sets of magnetic field lines being formed. So you have these poloidal coils here, which are loops of wires that run around sort of these, how do you call them? These shapes surrounding the toroid, and these produce your magnetic field lines that run around the donut, circumference, as it were. It's in the evening. You also have a magnetic field that gets produced from a central solenoid. So you have this solenoid, this coil in the middle that has currents running up that produce your magnetic fields that actually follow the shape of these blue coils on the outside. And so the sum of those give you a field that looks like something of these darker blue. It's essentially going to be following but slightly twisted as it's going around. And so your plasma will be flowing around the donut shape and hopefully being confined and not allowed to expand out too far, otherwise it might hit your walls and then you get issues. Now, yes, issues is one way to put it. Yeah, you don't want something at 100 million degrees centigrade going off and hitting your walls, and we'll see some photos in a minute. But we've got 2 very famous tokamaks shown in the photos on the right here. One is being built at Commonwealth Fusion Systems, Commonwealth Fusion Systems over on the East Coast. It's a spin-off company out of MIT, and so they're actually turning on their tokamak next year, which will be incredibly exciting to see the results there. And they also have a tokamak that was running over in the UK at Cullen Centre for Fusion Energy. This one's called JET, and actually JET had been running for many, many years, but has now been decommissioned, and so isn't in operation, as they're building another tokamak that I'll introduce you to in a few slides. There's another type of magnetic confinement fusion device that I wanted to introduce, which is called a stellarator. And stellarators, I think, have one of the most beautiful structures. It's incredibly complicated, not particularly easy to engineer and to build, but they have these plasmas that would be following the yellow lines here, and your magnetic field lines would be wrapping around as shown by, or the coils, I guess, would be following the blue here, and then giving you magnetic field lines that would follow the yellow. So an incredibly complicated geometry, but actually the stellarators give an awful lot of promise in some of the simulations that they've run of these. And they've got a accelerator that they're building over in Germany at the Max Planck Institute called Wendelstein 7X, which is the largest accelerator in the world. So that's another space of MCF, magnetic confinement fusion, that is incredibly interesting. Now, this is actually a video inside an MCF machine where they have a plasma running. Okay. For some reason, I'm afraid my videos are not working today. Anyway, what this video would be showing.
It might work
Yes.
if you go out of presentation mode.
Let's have a go.
I hope I didn't ruin everything for you.
It's still not even in this. But anyway, essentially this video was meant to show, oh no.
I'm keeping my mouth shut now.
It's alright, I don't know. I've had other PowerPoints where this is shown no problem. Oh dear.
See, now you have to fix it.
I've broken one
What-
thing. I should leave now with my throat.
It's alright. We'll get it back. My laptop can be a little temperamental. I think it thinks I'm teaching. Oh dear. Okay. Oh. Yes. Okay. Right. Anyway, in this video, essentially what it would show is that you don't really see the plasma rotating around as such, but what you do see is some regions of brighter flashes. And brighter flashes are actually not great because it means that the plasma is going out, getting hot in certain areas, probably hitting the wall in certain areas. And this is exactly what we don't want to be happening. We want those magnetic fields to be bringing the plasma in and confining the plasma versus that really hot plasma getting up against your wall. The other problem is that when the plasma starts hitting the wall, it starts to bring in material from the wall. And when you get that, it kind of acts to like dilute your fuel mixture, and it also ends up emitting a lot of X-rays. So you then end up losing energy, and it's just not ideal for your reactor at all. The other challenge in these systems is if you do have these instabilities, these flashes that are going out and hitting your wall, you're probably going to be needing to do some maintenance. But we do, as I said, end up with some small radioactive waste. There is radioactivity within these reactors that you can't just send people into the reactor to go and fix things and to go and switch out part of the wall panels if they're damaged. So actually what they need to use are robots. And indeed over at JET, at this reactor in the UK, they had robotic arms that people would be trained up to use. They actually used to train their operators by playing Jenga. So people would be playing Jenga to make sure that they got really good at handling the robotic arms. But yes, you could then go and take these robotic arms and go and use them in the reactor to change various components without having to send a person in. So it's another thought that a fusion reactor needs to consider is how are they going to perform their maintenance of their machines. Now, in terms of MCF, they have also been thinking about how they're going to scale up to an actual commercial size fusion power plant. So JET, the reactor over on the left here, is the one that was built in the UK, had a diameter of 5.92 meters and a volume of 80 meters cubed, but it didn't really produce that much power. So they're currently building a machine called ITER down in the south of France, which will have a larger volume of 800 meters cubed and be able to produce more power. And then the next stage after this will be to go to a demo reactor where they go to volumes of 1,000 to 3,500 meters cubed and produce even more power. And this is starting to get to steps that you would need to see with a fusion power plant. Now, ITER has actually been built for a little while now down in France. as with experiments, as with buildings, you sort of run into issues, you run into finance challenges. So the cost at the moment has been 15 billion euros. In comparison, the Large Hadron Collider in Switzerland cost $4.5 billion. So it is an extremely expensive project, but it is involving 35 different nations worldwide. So it's an amazing collaboration of research coming together to actually build this machine and hopefully see the operation. And actually, this is what ITER is starting to look like now. This is where they would have the tokamak inside, and you can see as a model of the tokamak here, and a little person is right down the bottom here. So you can start to see these are really, really large machines that they're starting to build. So that's looking at the magnetic confinement fusion, where you're using your magnetic fields to confine your plasma. Another approach is inertial confinement fusion, where you're actually using the mass of the fuel to stop the plasma from pushing out. And this was the approach, or this is the approach that's being investigated over at Livermore on the National Ignition Facility. So this was work that I was part of. So down in the bottom left-hand corner, we see here a photo of the NIF building, which is the size of 3 football fields. And I don't even need to say American football fields here, because football is American football, it's not soccer. And you can see here, this is the inside of the NIF chamber, where we have our targets, where our lasers will all be shooting through into. And so this is a 10-meter diameter chamber, so a really large site to be containing our fusion products. Our fusion reaction, as we'll see, the fuel itself is tiny. But at the NIF, the National Ignition Facility, we have 192 laser beams, which deliver 0.5 petawatts of energy, so 2 megajoules, in a few nanoseconds of time. Now, this is sort of that photo with the 3 football fields of the NIF building, and these are where most of it is all of the laser chains. So those 192 laser beams being created and amplified up in energy. And then you have the laser beams all coming through to your chamber where you have your fusion fuels. Now, if I'm talking about 2 megajoules of energy, that probably doesn't mean a whole lot in terms of, well, what is that comparable to? Well, you can find 2 megajoules of energy in your local grocery store. It's the amount of energy contained within a Snickers bar. The important thing to note here is that it's the time that amount of energy is delivered in. So you're delivering 2 megajoules of energy in nanoseconds. If you ate a Snickers bar in a few nanoseconds, I'd be very impressed. But you would also start to see some very interesting effects happening, which is what we see when we fire this laser with this amount of energy into our fusion fuels. So what happens is that when you produce your lasers, you have your fuel, you will focus the lasers onto the exterior of the fuel, and it heats up the outside of that fuel capsule. When you've got something that heats up, it likes to expand. And so you have the outside of the capsule that starts to expand out. And because we have something that's moving in one direction, Newton's law says you have to have something moving in the other direction. You have to balance those forces, those motions. And so the plasma expanding out launches plasma expanding inwards, or material rather expanding inwards, that starts to compress down. And as it compresses, when you start to push something really, really small, it starts to get really hot, really dense. You've now started to increase the amount of deuterium and tritium nuclei that are all close together. And so now there's more of a chance of them bumping into each other and actually sticking and fusing. And so that's the point where you hope to get to ignition, and then you hope to launch a burn wave, which is essentially those helium particles that we produce there as well are going to go out and help heat and create higher and higher temperatures to create even more interactions and even more fusion events occurring. Now, all of this is happening within these tiny little targets. So on the NIF, we use something called a hole ram. And so hole rams, there's a photo of one showing up in the top left photo here, and sort of an impression of what it would look like on the interior, where you have these laser beams that would be coming down into this hollow cylinder. So hole ram actually means empty room. It's not an empty room. Right at the center is a fuel capsule, and you can see a photo of a fuel capsule over on the right here. They're absolutely tiny. These hole rams are about 10 millimeters in length. When these lasers come through, they hit the wall, they actually create X-rays. And the X-rays are actually going and heating the outside of the capsule that then blows off, that then launches the compression. You can also put the lasers directly onto the capsule as well. That's an approach that's being investigated over the Omega laser over in Rochester, but the NIF uses these hole rams. And there are advantages and disadvantages to both kind of schemes to be using. But on the NIF, we've gotten some really exciting results, and actually fusion in general has gotten some really exciting results. So in August of 2021, we used 1.3 megajoules of, we produced 1.3 megajoules of energy from 1.05 megajoules of laser energy being put into this system, into this hole ram rather. So we've produced more energy out than we put in with the lasers, which means that we've created fusion. We've started to get this gain that we're looking for. We want to start creating this higher energy than we put in. In December of 2022, we produced 3 megajoules of energy, and we only used 2 megajoules of lasers to drive these systems. In 2024, repeatedly, we've seen 5 megajoules being put out, and actually earlier this year, they produced 8.6 megajoules of energy coming out of these interactions. So it's absolutely fantastic. It was really exciting. I was over it. I was working on the NIF when we started seeing these ignition results, and I came in the morning after the shot had happened on the NIF, and these donuts were all out in the corridor, and it was like, why are there donuts? And someone was like, I think there was a really exciting shot last night. And then everyone got really busy sort of doing all the analysis of all the data to be like, was it really a really high yield shot? Like, because you don't want just to be looking at one diagnostic result. You want to check lots of results to make sure that it's not just an anomaly, and then you can start to piece together the picture of what actually occurred. And so slowly then over the week, as the different diagnostics were analysed, we started to realise, yes, we've hit something really exciting here. And it becomes a little bit interesting when you talk to some of the MCF people about the results from the NIF, because over on JET, they have also been seeing some really large amounts of power coming out from the tokamaks. So they've produced 16 megawatts of power from 24 megawatts of heating. And a lot of the time in the fusion community, we'll talk about these Q values. And a Q value corresponds to the energy in divided by the energy out. And so on a tokamak, they said they had a Q value of 0.67. Well, the first laser shot, or the result that we got of a burning plasma in August 2021, we're starting to see Q values essentially of more than 1. The sticking point is what do you count as your energy in? Do you count it from plugging it in at the wall, or do you count it from another point? And in lasers, in ICF, we count it from the energy that we're putting into the hole ram. If we count it from the amount of energy that's actually being used to produce the lasers from plugging in at the wall, we are not efficient at all. But equally, we're using lasers that are decades old technology. If you used a computer from the 70s or 80s, you probably wouldn't expect it to be that efficient either, compared to what you might be able to do now if you went out and bought the latest laser versus these older lasers. So we count it from the energy that we're putting into our hole ram. With a tokamak, it's slightly harder as to where to define that energy. But equally, they have had these really exciting results of producing an awful lot of power and sustaining their plasmas as well. Because the other thing is that essentially when these plasmas are flowing around the tokamaks and you get these instabilities or you get these bursts that are going out and hitting the wall, that is not good for your plasma, and you'll actually end up going to, it's kind of like a candle. It will end up sort of flickering and going out. So you want to sustain that plasma and those fusion reactions for as long as possible, that confinement for as long as possible. That's really the trick for fusion, to give it as much chance of colliding with another particle. So, and this is looking at then some of the scales from the NIF, so looking at these different ignition experiments. So we've got the experiments from 2022 out to this year, so June this year. And you can see that there is variation across this graph. So the red bars are showing the laser energy that's being put into these whole round targets, and the lighter coloured bars are from the amount of fusion energy that's coming out. And so you can see there is a little bit of variation, but generally we are producing more energy out than we're putting in. And there's been an awful lot of work that has gone into getting these results and understanding the bits of physics, but yeah, it looks like we're moving in the right direction, and generally there is an understanding of what has caused this variation on each of these shots too. So this has really been looking at a lot of the physics and how are we going to confine our plasma to start with. But what then happens, so we've got this neutron coming out. How are we going to use that neutron to create us energy? How are we going to drive and connect up to the power grid? Because you need to use that neutron to actually be then helping to drive your steam turbines. The other thing we also need to be doing is breeding tritium. So we said that we need tritium, deuterium and tritium as our fuel in fusion, but we've got to make tritium. And we've got to make tritium from the lithium, the laptop battery. And so what is being proposed by a lot of, when you look to designing a commercial fusion reactor, you would have a lithium containing blanket region where you put your lithium atoms surrounding the reactor, such that then when those neutrons are streaming out, they are interacting with this lithium to then give you tritium. In doing so, they're also going to give you an awful lot of heat. You can start to then have some sort of heat transport or heat exchangers carrying some sort of,
Do you really feel okay about questions now?
Yeah, absolutely. I should have said, please ask questions.
I'm imagining, I've never seen a lithium blanket, but I take it it's spherical, and it surrounds the chamber.
Mm-hmm.
But then again, these lasers, hundreds of them, have to get through the lithium blanket. Is this tricky?
Yes.
Oh.
Yeah. No, this is exactly it. So ideally, you'd love to cover the whole reactor, that whole sphere with a lithium blanket. But if you've got lasers that you've got to be shooting through into your chamber, you've got to have ports for them to come through. Also, neutrons are really good at interacting with materials and damaging materials. And so, how long are those materials going to end up surviving for? There's a lot of tests going on to try and understand this. Are there then other schemes that we can be using, perhaps changing the amount of lasers, for example, that we need? Or what you can start to do, and I have another slide in a minute about this, is some of the private fusion companies that are being set up are looking at, okay, well, let's make our chamber even bigger, so that then you have more space, more surface area where you can have your blankets, and that helps with then some of these neutron loadings out here. But there's a lot of different ideas. Also, I should mention that deuterium and tritium is one fuel that you can use to do fusion. There are other fuels that you can go out there and use to fuse and give you energy. The challenge is that deuterium and tritium has the highest likelihood of occurring at a fairly reasonable temperature. Other fuels have a lot lower likelihood and often need a lot higher temperatures to actually get you to your fusion conditions. So some of these other fusion reactors don't produce you a neutron, but they might produce you other products that you can then also be harnessing. But they are harder to actually get to. You end up with other issues that come about from some of the other schemes too. Yes?
On the previous slide, there was a highest spike in April of 2025. Is there any particular reason, or are there factors that make it so?
Yeah, so in April this year, they actually started changing the design of the fuel capsule itself. So within that whole RAM, you've got the fuel capsule in the middle, and they changed the design of some of the exterior of the capsule, which made this massive jump. That with each of these shots, they've been playing around, changing different variables. Because on the NIF, we're only getting really one shot a day. It's very hard to do a lot of repeat experiments. But slowly we've been building up an idea of what matters, what's important in driving these fusion conditions. And so they changed the way that that outside layer was structured such that it gave a much nicer implosion. Because one of the other issues is if with sort of laser-driven or X-rays driving your fuel capsule, is if you imagine, if you have a balloon, I should have brought a balloon in with me. If you squeeze the balloon in from the sides, it's going to squish out the ends. So you want something that gives you a nice symmetrical implosion such that everything is imploding in the same way. That's been one of the challenges that we've encountered in doing ICF, is getting this nice, smooth, symmetrical implosion. We also end up seeing instabilities too, and I'll show you, I've got a picture of what some of those instabilities look like as well.
Thank you.
Yeah.
Yeah, I noticed the very end value there seems to drop off. What happened there?
That's a good question. Actually, I don't know the answer to this one. I don't know what happened on that shot in June of this year as to why it dropped down. I will have to go and ask my colleagues at Livermore. Yeah.
Have experiments been tried with pure tritium?
With pure tritium itself, I don't believe there have been. I guess looking at there's a plot of all the different cross sections investigating the different fusion reactions. I can't remember where the TT, the tritium interaction would sit on there. I mean, to be fair, within a DT implosion, you will still have DD reactions, the deuteriums interacting and fusing with the deuteriums. You will also have the tritiums fusing with tritiums. It's just that the highest probability occurs from the deuterium and the tritium, that they're most likely to come together and fuse. But you will still get a small fraction of these others. But for a pure tritium implosion, I don't think it's been something that's been explored. Yes?
Using lasers as a generic term for light amplification, there are many types of lasers. What kind of lasers are being utilized for this?
So we use lasers that produce us a wavelength of, I think, 352 nanometer light wavelengths. Another challenge with laser light is that as it's propagating into a plasma, there is a density that it can reach. It can only get so far into your fuel. And you want your laser to be propagating and heating as far into the fuel as possible, because it will be depositing heat the whole way as it goes through. It will be absorbed by that plasma. So the further you can get into the fuel, the better. And so we've been using these lasers of 352 nanometer light to get in to that fuel as far as we can. The challenge is that as you're producing this laser light, we produce laser light at about 1 micron wavelengths, and then you have to put it through crystals to start changing the wavelength. And when you start putting it through these crystals, it actually starts to lose energy in that process. So you end up losing the energy that you originally put in, you start to lose even more so then. Okay, so as I just touched on a little bit, what have we still got to look at in actually producing these commercial fusion reactors? Well, for one, you've got this chamber that if we want to do, for example, inertial confinement fusion, we need to be shooting our fuel capsules 10 times a second to get the amount of energy out for a commercially viable power plant. And so you're going to be needing to drop these fuel capsules in 10 times a second. You're going to be needing to track them. And at the moment on the NIF, we're shooting once a day. Equally, the NIF was not designed to be a commercial fusion reactor. So there are companies out there exploring technologies and looking at how you might then have these fuel capsules falling in and being able to then fire them as they reach the center of the chamber. One concern is that these are some of the optics that are called the final stage optics, the very last stage that the laser will pass through before they then enter the chamber. These are pretty large optics that will be experiencing damage by these neutrons as they're coming out as well. Within the tokamaks themselves, as I mentioned, you've got this blanket that's going to be surrounding your reactor as well. You've also got wall materials in here that we need to understand how those are going to be responding not only to the neutrons but also to the heat, that these are incredibly hot environments. And actually this is a photo in the top middle here of some of the damage that can be done by neutrons. We can also see some instabilities here in the top right. So as well as trying to squish it uniformly and symmetrically, you can also end up something called mix. So you start to get bits of material mixing in from the outside of your fuel capsule into the center, much like with the tokamak. When the tokamak is bringing in material from the walls, that's getting in and mixing in and being detrimental to your fusion and to the temperatures you're reaching, you have similar kind of mix occurring and getting into the plasma and the fusion conditions at the center of your fuel capsule as well. So these are a little bit of some of the things and some of the questions that we still have to address. But actually there's a whole load of private fusion companies that are popping up. So this is a plot that I've gotten from Giant, where they've listed out some of the different approaches to fusion, so magnetic fusion, confinement fusion companies, inertial confinement fusion companies, magneto-inertial confinement fusion, which is this pulse power approach to looking at creating fusion. And there's a lot of really interesting and exciting work that I think are going to come out of some of these private fusion companies. There's a lot of different approaches, a lot of different thought going in into, okay, how are we going to design our blanket? How are we going to work with all these lasers that are coming in from different directions? Or how are we going to surround our reactor with magnets that are going to be helping to provide this confinement? And there's an awful lot actually that are based within the Bay Area as well. Which is, wonderful to be able to work with some of them too. And actually, if we look at the amount of investment that's been going in by the different locations across the world, you can see how things have started to change. That, particularly, I guess, with some of the results coming out of the NIF, for example, you could start to see some of the spikes in the private industry that, okay, maybe fusion actually could be back on the map again. Maybe this is actually a viable option once more. So yeah, it's been awesome to see this, and I'm hoping now with more investment and more interest and more facilities coming up, more exploration, that I think the fusion landscape is going to be very exciting over the next few decades, or I think even within the next decade, we'll see some exciting results. And as well as a lot of the fusion experiments that we can be doing, and the research we can be doing in understanding fusion, it turns out that 99% of our observable universe is actually made up of plasmas. And so you can use these facilities to do a whole range of other experiments as well. And so I've explored some of these myself. So we can investigate astrophysical jets. We can look at accreting star pairs. We can look at instabilities being created out in the universe as well. My thesis project for my PhD was on looking at magnetic reconnection, the same process that causes the northern lights. You can have a look what happens when you have a supernova exploding. They launch out these shock waves. What happens with those shock waves? Could they be producing the high energy cosmic rays that we see that we can't really explain? And then we can also be investigating turbulence, which it turns out could also be giving cause and reason for the reason magnetic fields exist within the universe, because there weren't magnetic fields at the very start of the Big Bang. So where have they come up from? So there's a whole load of really cool laboratory astrophysics experiments we can do as well using some of these fusion facilities. So in summary, hopefully I've been able to show that fusion is an exciting landscape that will hopefully form a part of the answer to future energy resources. There are still challenges to address, but with a growing field and investments both financially as well as actually the workforce, we're getting an awful lot more interest. I see an awful lot of students who are very interested in engaging with the fusion research field. We are making great gains, also pun intended on gain, the Q values that we're seeing from fusion. And yeah, in the meantime, there's also a wealth of exciting phenomena that we can be learning about. And so, cheers for listening. And any questions?
You mentioned that you're starting your lab at Cal. That means you're trying to recruit would-be PhD students?
Yes.
And is it specifically in a type of fusion? Is it working on inertial confinement?
So a lot of my work is still working on inertial confinement fusion. So I'm very interested in looking at some of the diagnostics that we're trying to use to understand these reactions, as well as I am studying some of the magnetic fields being produced in the plasmas themselves. So the plasmas also produce fields. So we're trying to understand some of those dynamics. So yeah, looking at recruiting PhD students. I also have an awful lot of undergraduates come along wanting to learn more. And I think it's fantastic. I actually really love the US system where students can come and be very engaged from very early on in their time at university in research that's going on in the university. And maybe sometimes you go along and try a research project and it's not for you, but you don't know if you don't try. So, yeah. Yes.
So you talked about anyway, these neutrons are shooting out that
Yes.
you want to capture that have the energy.
Mhm.
How do you capture that and convert that into usable
Yeah.
in the energy grid? And send it out to, through the wires to get to homes or whatever. How do you convert that?
So the neutrons, as they're passing out through outside of your reactor, as they're passing through water or as they're passing through certain materials, they are going to be slowed down. And as they start to slow down, they're depositing energy. So in slowing, they're losing energy, and when they're losing energy, they're depositing it to their surroundings. And so you can start to use those slowing down of the neutrons to be then depositing energy and taking that energy heat to use to heat your water to then drive your steam turbines. Yes.
I know there's not particularly an answer, but do you expect to be a winner? Not you, but I mean inertial or magnetic,
If I were to put money on it.
and everything else will just fall away?
So I think having now experienced the pulse power facilities at Imperial College as well as the laser driven, I have a personal bias to wanting to combine both, which is what this magneto-inertial fusion approach does. It's using pulse power as well as potentially lasers, or maybe you'll use another driver. So yeah, they're using magnetic fields to actually compress down the fuel. So rather than using it to just confine it and hold it away from the walls and just hold it in a volume, they're actually using the magnetic fields to push everything together. And you can also start using lasers to give you some additional heating and additional help. So I really like that approach. Yes, there's so many out there. Yes.
Being that magnets are so intrinsic to the success of this, is there research being done to develop new magnetic materials?
So magnets are important for the tokamaks. They're not for inertial confinement fusion, but actually, one bit of technology that has been looked at an awful lot at the moment, they use superconducting magnets. And superconducting magnets have to be kept at very, very cold temperatures. Again, we said plasmas, fusion is going to happen at very, very hot temperatures. So if you've got magnets that need to be held at very cold temperatures near something really hot, that's not ideal. So they've been developing magnet technology, superconductors that are actually at higher temperatures and can start to operate better at a higher temperature. It's still not that higher temperature, and this will be some of the tests that I think Commonwealth Fusion are looking at with their magnet technology. But yeah, there is an awful lot of work going on to that as well. Was there? Yeah.
The magnetic confinement, does most of the energy in go into just the magnetic field, or is the other component just the acceleration?
Yeah, so there's different energy in that goes in. So you're putting energy into creating the currents that then create your magnetic fields. There are also, they sort of kickstart the heating of the plasma, the fusion conditions, by different mechanisms. So sometimes you can do neutral beam injection, so you'll be accelerating beams of particles through your tokamak to then collide and produce you heating, or other mechanisms as well. So yeah, there are other sources of energy in as well as the magnets, but that is an awful lot of, a lot of the energy will be going into ultimately just using the power for the magnets. Yes.
You mentioned that Q number, the energy in versus energy out. Do folks in the field yet have any estimates of what that number might need to get to have a hope being a viable power source?
Great question. So thinking about the Q value of the different fusion reactors, the Q value will actually need to change depending on what fusion path you're using. Because, for example, the ICF fusion is almost like a pulsed operation. It's not a continuous operation. You want a certain amount of energy to be produced per second. So when you actually go to looking at, well, what amount of energy do we need from each interaction, it's a different value than comparing magnetic confinement fusion, where it's a constant fusion process going on for, hopefully you would confine your plasma for as long as possible. So it's different Q values because the energy is always being produced continuously or instantaneously. But yeah. Yes.
Yes, actually, I was at the NIF in 2009. Way back, was a field study between the University of California and some Danish universities. But at the time, I would bet my last dollar they were using palladium as the target. And if I'm misremembering it, that's totally fine. But has there been, like, in narrowing down the deuterium-tritium combination, like the process getting to that, has that been a very winding path, or was that kind of known up front?
So for creating fusion implosions, for creating energy out, you want to be using deuterium and tritium. That would always have been the fuel that they had for looking at fusion. Some of the different materials that they've been changing has been, so as I said, they heat the outside of the capsule. And the outside of the capsule, the fuel capsule, that blasts off, that then launches the compression. Those materials have been investigated and played around with, so they've gone with carbon, they've gone with plastics. They've also explored different materials for the whole ram itself. So that cylinder where the lasers are coming in, hitting the cylinder, producing X-rays that are heating your central fuel capsule. That's also been a material they've changed with some different cocktail materials. Often the primary material that's being used is gold, because gold gives a X-ray spectra that is very good for heating the capsule itself.
So is it with the capsule that the material's in, is the shape of it more important, or is it the X-ray capacity?
So the shape of, so you have these spherical fuel capsules in the center. So you want to implode it nice and uniformly, which means you want your X-rays to come on nice and uniformly as well. They have also seen that the structure like how smooth your capsule is can also affect the implosions as well. It's kind of working out what is the most important, what can you sort of trade off a little bit, and these are some of the balances that people have been working on over at the NIF with all the different models and all the different tests and things that they might tweak in an experiment to work out what is the optimum. And also, I guess then going forwards to a commercial fusion power plant, what is it that we can get away with being the best case, that we don't need to be getting the optimum of everything, but what is our best case and what sort of things can we have a little bit of tolerance and a bit of error in for working around. Yes?
Nuclear reactors create waste. You know, you've got radioactive water. What do these units, what kind of waste are they creating?
So the neutrons that are coming out, a lot of radioactive waste comes from those neutrons coming out and interacting with materials and giving you radioactive materials. And so we've got neutrons still coming out of our implosions as well, our fusion reactors. And so it depends what materials you use to surround your reactor. And a lot of that is still being determined. But you will still get materials that become radioactive that are surrounding the reactor itself. But it's in much lower quantities and for much shorter half-lives. So you don't need to come up with these plans to be storing the radioactive waste for long periods of time. It'll be sort of 100-year half-lives versus thousands of years of half-life. Yeah, and as I say, it would depend on what sort of materials we determine are the best ones to be putting outside. And considering radioactivity is one of the things that are included in trying to work out what is going to be the best materials for surrounding these reactors with.
But the neutrons that are given off, they can't be recycled or recaptured? Or?
Neutrons are a really fiddly particle. They have no charge. And so with charged particles, it's really easy to control them, like we do with the plasmas, charged particles. You put some magnetic fields, you can start to steer them, put them where you want them. Neutrons just fly out. They're neutral, so the only way of stopping them is putting something in front of them that makes them slow down. You've got to put some sort of material there. They are a pain. They're great, but they're also a pain. Yeah. It'd be nice to focus neutrons. If anyone works it out, then please share. Yes.
So it seems that with energy, producers of energy, you want to get the biggest bang for the buck. I mean, at the beginning, you showed oil, you showed solar, and so you want to get the biggest bang for the buck. But what I'm a little confused about is, isn't it has to do with like conservation of energy. I mean, do we have like, I'm just a little confused. You're putting in a certain amount of energy to get even more energy, but where is that coming from? And is, maybe you can just discuss what I'm not doing such a great job at.
Yes, so I mean with any form of energy resource, for example, when you burn oil or gas, you are releasing energy from those particles in some sort of form. So whether it be a chemical release of energy or whether it be a nuclear release of energy in the nuclear power plants. And there's something called energy density. So when you take a volume of fuel, when you do something to it, how much energy can you get out of it? And when you're comparing things like gas or oil, they aren't particularly energy dense in comparison to fusion power or fission. That for a much smaller mass of fuel, you can get way more energy out. And that's just because the energy is stored in different ways, and you're manipulating your atoms in different ways to release the energy that's already being stored there. It's just we have to do something to get it out. And so one of the considerations, I mean there's lots of considerations, and when you're choosing the different energy resources, you're considering, okay, well, how big a space am I going to have to occupy with producing this energy? But also there will be other factors of what is this doing to the environment around? Is this a suitable environment for this to be within? Like, are we going to put our solar power plants here? Solar panels? Are we going to want a nuclear reactor in this area? There will be lots of different considerations and different decisions that you'll be making in working out what is the optimum power resource for those areas. But yeah, it's all to do with the energy density, that when you take a volume of fuel, it's already kind of contained within it, depending how you change it, how much energy you can get out. Yes?
First, apologies again for my suggestion. I didn't mean to terrorize you.
That's okay.
Just getting back to a non-technical question about safety, and if you could kind of put your forward-looking hat on and just say, one of these technologies will be industrialized. But right now, I think we know with fission reactors and industrial fission reactors, they certainly can fail, and they're catastrophic when they fail. Or they can be catastrophic when they fail. And my question to you is just really simple. If you look forward, what would a failure of a fusion reactor look like? How bad would that be?
So this is something that's, looking at failures of the different power plants. You have put in a certain amount of fuel into each of those interactions. So for example, in ICF, they know how much the maximum amount of energy that you could get out from that capsule. If you entirely burnt the whole fuel, how much energy is going to be released? And can your chamber contain that? And so that is something that gets factored into thinking about when you're designing these reactors, that, if you release that amount of energy all in one go, will it all still be contained? And the answer is, for the designs currently, yes. And I don't think you'd want to go above that, because otherwise then you're destroying your power plant itself. So that's already, I guess, an inherently safe constraint that is going to be put onto these reactors.
I guess when you're talking about needing temperatures well in excess of the temperature of the sun, that we're talking about like very small volumes where that's happening, or very large volumes where that's happening?
Very small. Well, so it's very small volume. Obviously, again, it depends on the approach. So you've got, in MCF, you've got these very large volumes of very hot plasma that are right close to your walls. In an ICF implosion, you've got a very small centered mass, but actually that's going to expand out sort of after you've imploded it, then everything wants to push apart and will explode outwards. But as it's expanding out, you are losing some of the heat, as it were.
Thank you. I appreciate it.
How do they refuel tokamak reactors?
So with tokamaks, you can constantly be replenishing and putting in additional fuel. So they have, down the bottom, they have what's called a diverter. And so diverters you can use to sort of siphon out some of the impurities that you don't want cycling around and mixing into your reactor. We also have injectors that are injecting these neutral beam particles, which actually then can become part of the plasma as well. There are various injection methods that you can have in tokamaks. Yes?
You haven't talked about geologic hydrogen as an alternate energy source. According to CNN News earlier this year, there's enough mineable hydrogen to power the Earth for the foreseeable future. So you don't need lasers and you don't need tokamaks. You just need some mines.
So I guess, so you're asking about whether hydrogen would be a possible fuel source as well. The challenge with hydrogen, I guess, is that it's quite a volatile gas, that you wouldn't, for example, necessarily want a hydrogen-powered car. Equally, I guess you wouldn't want a fusion-powered car either. To be fair, I don't know a huge amount about the hydrogen fuel resources. Beyond that, it's more of a volatile power source.
It's a lot of investment money going into it.
Yeah.
Just curious, what role, if any, is artificial intelligence playing in the development of this?
Yeah, great question. So yeah, how are we thinking about using AI and trying to help us push forwards with fusion? So one big tool that's being talked a lot about now is digital twins. So creating a complete power plant and modeling it with essentially sort of AI tools, where you're starting to learn about all of the different components and how everything's going to fit together, and optimizing the entire system versus just individual components, and doing your experiments on just one or two different variables, or however many variables you want to be changing, but actually trying to learn about the system as a whole. Now, the challenge with AI is that if we don't have an understanding of some of the physics out there or some of the processes, AI isn't really going to get there in predicting it necessarily. There's an awful lot that we've got some really good simulation and modeling codes out there to try and understand fusion experiments, and actually a lot of experiments initially when they were set up, the model said it was going to work like this, and you do the experiment and it didn't work like that at all. So I think AI will be very powerful in helping us understand our experiments and our but putting in all the knowledge that we have so far. But in terms of starting to predict the areas that we don't know, we're still going to have to do those experiments and those tests alongside of building up these models and trying to optimize in parallel. So that's where I think it will be really instrumental.
So when you mentioned deuterium power, the problem is you have to source it directly from the ocean. Now the thing is, when you have climate change blended into the picture, how will deuterium be sourced as a potential energy source when you have climate change causing, sea waters to rise in temperature, and how will that affect, potential deuterium for energy?
So as far as I understand, when we're looking at extracting deuterium out of seawater, the other environmental effects such as the changing sea levels, the temperatures, are not going to affect the amount of deuterium in the water. That will still be a constant. And actually, if you run the calculations of how much deuterium we're going to need, the sun will actually burn out before we run out of deuterium in seawater. So there's a hell of a lot of atoms that turn out in seawater. It's great. We're good.
Maybe one last question?
Yeah, one last.
What was the name of that book that you mentioned at the beginning?
So I actually have it in my bag. It's Physics for Future Presidents by Richard Muller. Would recommend. I'm not on any advertising for it, but I think it is a fantastic book. Especially, I think, when their questions are around nuclear fission and actually the risks, as I say, associated with these accidents, where it lays out things incredibly well, looking at when you have these disasters, how much of a disaster is it, and when you start looking actually in the environments we live in naturally, there's an awful lot of radioactivity out there that maybe the nuclear power plants aren't as big of a risk as we think they might be.
One more?
Okay, one very well.
I just want to make a comment. The question about hydrogen, Mueller's book mentions a lot about that too as well.
Oh, interesting. I haven't got onto that section yet. I'm still reading it, so yes, okay. He addresses hydrogen as well. Awesome.
I hope Dr. Tubman will forgive me if I give you a little statistic here that I think is helpful. The various reactions we're used to studying in chemistry involve the electrons of atoms. So whether we're burning hydrogen or burning coal, burning gas, that involves the electrons, and that's fundamental to all chemical reactions. In the nucleus, we're dealing with nucleons, neutrons, protons, and those guys involve forces that are so much stronger that every typical nuclear reaction, just between two particles, is typically 1,000,000 times more energetic than an electron reaction, a chemical reaction. And I think that's when Ellie talks about energy density, maybe at the heart of that issue is the fact that these nucleons, these particles at the heart of every atom, are just mighty. And for us to ignore them, not use them, at least try to, even though it may always be 20 years off. Yes? Well, we got to still try. Yes. Before we give our speaker a final round of applause, let me remind you, Tuesday, August 26th, 2 weeks from tonight, my weird encounters with insects. Yes. Please join me in thanking yourselves, thanking Hop Monk, and most of all, Dr. Ellie Tubman.